3. I-Atlas should be a quiet, cooling comet by now, 186 million miles from Earth, running on a trickle of sunlight. Yet the sharpest new images reveal impossible, laser-straight twin tails and a density far beyond what physics predicts. Even Avia Loeb's calculations cannot explain why the anti-tail is 1 million times denser than the solar wind. So, what is this object really doing in our solar system? 186 million miles from Earth, sunlight falls weak and thin. Just 300 watts per square metre, a fraction of what reaches our planet. This is the deep, outbound track of 3I Atlas, an interstellar comet now drifting through the cold outer reaches of the solar system. At this distance, comets are supposed to be winding down. The heat that once drove furious jets and streaming tails should be fading. Most comets, after rounding the Sun, slip into quiet. Their activity drops, their brightness wanes, and their tails shrink as the Sun's energy falls off fast with distance. But 3I Atlas did not follow the script. Even before it neared the Sun, telescopes caught it acting up. In May and June 2025, NASA's TESS satellite recorded the comet already active at 644 astronomical units from the Sun, nearly 600 million miles out, where solar energy is just a trickle. Standard comet models say water ice cannot sublimate at such distances. It is simply too cold. Yet 3I Atlas was already brightening, already shedding material into space. That early outburst hinted at a deeper puzzle. The energy environment was wrong for such behavior. Instead of waiting for the Sun's heat to trigger activity, 3I Atlas was firing up in the darkness far beyond the orbit of Jupiter. The implication is that something other than water ice must be fueling its activity, likely carbon dioxide, or even more exotic ices that can vaporize at much lower temperatures. As the comet drew closer, the solar power it received jumped from less than 20 watts per square metre at 6.44 astronomical units, up to 300 watts per square metre at its current position. Still, that is only about a quarter of the energy Earth receives. For most comets, this would mean a gentle fade, a return to quiet. But 3I Atlas kept defying expectations. The comet's persistent energy, its refusal to quiet down, became the first sign that conventional comet physics might not be enough. Avi Loeb, a Harvard astrophysicist known for his work on interstellar objects, began analyzing the numbers. He focused on the mismatch between the solar energy available and the comet's stubborn activity. The comet was supposed to be calming down. Instead, it was ramping up, setting the stage for the next surprise, images that would reveal a geometry and structure never seen before in a natural comet. November 22nd brought the sharpest look yet at 3I Atlas. Through a half-metre telescope, astronomers captured a bright, compact coma flanked by two narrow tails, one stretching away from the Sun for nearly 3 million miles. The other, the anti-tail, reaching 600,000 miles back toward the Sun itself. These measurements held steady in a follow-up image on November 24th, even under poor sky conditions. Multiple observatories confirmed the same geometry, eliminating the possibility of camera tricks or processing errors. The tails themselves defy expectations. In most comets, tail material spreads out, diffusing into broad, wispy fans as dust and gas are battered by the solar wind and radiation. But 3I Atlas's tails remain astonishingly tight and sharply defined, their structure holding together over millions of miles. This laser-like collimation stands in stark contrast to the fuzzy, turbulent plumes seen from typical cometary outgassing. The effect is so pronounced that even amateur astronomers using far smaller telescopes reported the same needle-straight symmetry. The geometry presents a persistent 5.1 ratio. The away from the Sun tail is 5 times longer than the anti-tail, a relationship that has not wavered across repeated observations. The anti-tail's direction is especially puzzling. To maintain a stream of dust and gas pointing toward the Sun, the material must be dense enough to push back against the constant pressure of the solar wind. Here, Loeb's estimate comes into play. He calculated that the anti-tail's density must be about 1 million times greater than the surrounding solar wind. No standard comet process can explain such a concentrated, sustained flow. Normally, as the solar wind rams into ejected cometary material, it disperses and thins out rapidly. Yet in 3I Atlas, the anti-tail holds its form as if locked in place by a force far stronger than simple outgassing can provide. This is not just a visual oddity. The numbers force a direct confrontation with comet physics. Sustaining a 600,000-mile anti-tail at this density requires an engine that standard models do not supply. The result is a paradox, one that can be measured, not just seen. For 3I Atlas, the tails are more than a spectacle. They are a numeric challenge to everything astronomers thought they understood about how comets lose mass and shape their surroundings. Harvey's calculation starts with the numbers. To keep 3I Atlas as bright and active as observed, the comet must be losing material at a staggering rate, about 200 tons every second. Over the 2 months since perihelion, that adds up to billions of tons, roughly 1/10 of the comet's estimated total mass of 33 billion tons. The expectation is straightforward. At that pace, the comet's nucleus should be shrinking fast, or even breaking apart under its own mass loss. But that is not what the images show. NASA's Mars Reconnaissance Orbiter captured 3I Atlas as a glowing sphere, its coma stretching nearly 932 miles across. Inside that cloud, the solid nucleus is tiny by comparison, just a few miles wide, with a total surface area of only 30 to 40 square miles. Yet Loeb's math says that to sustain the observed outgassing, the comet would need about 620 square miles of actively sublimating ice. That is a gap of more than 15 times between what is needed and what is physically available. This is not a subtle mismatch. The numbers point to a crisis. The visible surface area simply cannot account for the mass being lost. Standard comet models would predict the nucleus to fragment, exposing new surfaces and creating a swarm of debris. But even high-resolution images from November 11th show a single, intact nucleus. No obvious fragments, no spreading debris cloud. The comet's coma remains smooth and bright, not ragged or chaotic as would be expected if it were breaking apart. The contradiction is stark. The comet is losing mass at a rate that should be catastrophic, yet it shows none of the signs of physical self-destruction. The surface area deficit remains unresolved, raising fundamental questions about how 3I Atlas is managing to drain so much mass without tearing itself to pieces. Spectroscopic data collected by JWST and Hubble in mid-2025 forced astronomers to confront an unexpected chemical fingerprint. The gas streaming from 3I Atlas was not just rich in the usual suspects, cyanide, carbon dioxide and water vapor. It carried a strikingly high ratio of nickel to iron, far exceeding what has been measured in any known comet, even the previous interstellar traveller, 2I Borisov. In fact, the nickel to cyanide ratio was so extreme that it sits well outside the range of solar system comets, resembling the proportions seen in industrial nickel alloys. The odds of this happening by chance, according to some estimates, are less than 1%. Polarimetric measurements added another layer of strangeness. When astronomers analysed how sunlight scattered off the comet's coma, they found a level of negative polarisation at small phase angles that is more intense than any comet on record. This signature is reminiscent of trans-Neptunian objects, icy bodies from the far edge of the solar system, implying a mix of dark and icy grains, unlike what is typically observed. Mainstream comet scientists acknowledge these values are unusual and they argue that interstellar visitors should be expected to surprise us. With only 2 previous interstellar comets to compare, the sample size is simply too small to define what is truly abnormal. The debate will not remain theoretical for long. On March 16, 2026, 3I Atlas will sweep past Jupiter at a calculated distance of 53.445 million kilometres, almost exactly matching the planet's Hill radius, the region where Jupiter's gravity dominates. This encounter is being hailed as a natural experiment. If the comet's trajectory or activity changes in ways that standard physics cannot explain, or if its chemical emissions shift dramatically, the data will provide a decisive test. For now, the clock is ticking and both sides are watching closely, waiting for Jupiter to weigh in. Right now, 3I Atlas defies every natural explanation astronomers can offer. As new data pours in, each unanswered question pushes the limits of what we call normal in our universe. Sometimes the rules we trust most are the ones most urgently in need of rewriting. What do you think?